It's pretty common for product teams to hit a wall when their carefully designed parts come back from manufacturing and they just don't quite fit together as intended. Or maybe they fit, but they're not really functional. It often comes down to how we communicate those critical dimensions and tolerances. Alex, in your experience on the shop floor, what's often missing there?
Yeah, that's a classic scenario, Mia. What's often missing, or at least not used effectively, is GD&T geometric dimensioning and tolerancing. Look, it's a system of symbols, really, that lets engineers and manufacturers speak the same language about a part's geometry. It's not just about this hole is 5 millimeters plus or minus 0.1 millimeter. It's about where is that hole supposed to be functionally relative to other features.
Hmm, okay. So it's less about the exact size of every feature and more about how everything relates and fits together. Is that the design intent I sometimes hear about?
Exactly. You've hit it right there. Traditional tolerancing with just coordinate dimensions, it often misses the functional aspect. GD&T is a functional description. It lets us detail precisely how a part needs to fit and work without having to overspecify every single dimension. That can save a lot of cost and actually improve quality. It's critical for interchangeability, especially in industries like automotive, aerospace, consumer electronics. You need parts to fit every single time, even with minor variations.
So it sounds like GD&T helps standardize communication, which I can immediately see the benefit of. What's the origin story of this system? Was it always around, or did it develop out of a specific need?
Well, it really got going during World War II. You had this Scottish engineer, Stanley Parker, who saw that traditional methods were causing perfectly good parts to be rejected just because their dimensions were technically out of spec, even if they'd function fine. He pioneered functional tolerances, which weren't purely about size. Then, the US military picked up on it in '49 with MIL STD. That was really the first GDTT standard.
Huh, interesting. From wartime efficiency to today.
Yeah, and it's evolved since then. The American Society of Mechanical Engineers, ASME, they developed their own standard, ASME Y14 Ballion 5. The latest revision, ASME Y14 Ballions 120 hour, that's still the guiding reference for most industries worldwide.
Okay, so beyond just better communication, what are the big advantages for, say, a product team working with us at First Mold? What benefits do they really see from using GD&T in their designs?
Right, there are a few key ones. First, like you said, communication. It spells out the design intent clearly. The focus shifts from just size to functionality. You use standardized symbols and what we call feature control frames, and that just minimizes misinterpretation. Take true position, for example. If you specify true position for a hole, everyone on the floor knows exactly where that hole should be and how much variation is acceptable. That means fewer errors, better quality control, and a more reliable product, you know?
So, it's like a universal language for manufacturing, preventing those I thought you meant this moments.
Exactly. And that leads directly to the next big one, cost efficiency. GDT lets you put tighter tolerances only where they're absolutely critical for function. For non-critical features, you can often apply looser tolerances. This drastically reduces production costs and manufacturing time. You're not trying to hold every single dimension to a super tight spec when it just doesn't matter for the part's performance.
That makes a lot of sense. You're not over engineering the non critical stuff. Can you give an example of that? where you might loosen a tolerance that traditional methods would have kept tight.
Sure, think about a mirror. With traditional dimensioning, an engineer might specify a really tight thickness tolerance to prevent warping. But a tight thickness doesn't actually guarantee a perfectly flat surface, does it? The surface could still be wavy. With GD&T, you'd specify a flatness control on the mirror's surface, and then you could relax that thickness tolerance. The part becomes much easier and cheaper to manufacture, but you still get a truly flat, functional mirror.
Oh, that's a great example. So the engineer is directly addressing the functional requirement of flat surface rather than just a proxy for it, like thickness.
Precisely. And this ties into the third benefit, functional and reliable parts. By specifying the size, location, orientation, and form, we call that SLOF. SLOF of critical features. GD&T ensures the part will function correctly in its final assembly. Even if individual dimensions vary within the acceptable limits, the overall functionality is preserved. Think about aerospace parts, like turbine blades. They operate in extreme environments. GD&T ensures those blades maintain their correct orientation and location relative to other components, so they function reliably under stress.
Okay, so improved communication, cost efficiency, and reliable parts. What about waste? Does GD&T impact that?
Absolutely, it helps reduce waste and rework. When design intent is ambiguous, manufacturers sometimes make parts that just don't meet functional requirements. Those parts end up scrapped or needing expensive rework. GD&T cuts that risk by clearly defining the acceptable tolerance zones for each feature. You know exactly what's acceptable and what isn't, which means fewer defective parts, higher efficiency, and less wasted material. It's a win-win.
So GD&T clearly offers a lot of advantages. You mentioned SLOF earlier: size, location, orientation, and form. Can you break down what each of those means in the context of GD&T?
Yeah, SLOF is the core. It's how we categorize what we're controlling.
Got it. So SLOF gives us the categories, and then we use specific symbols and chew control frames to define the acceptable tolerances. Can you explain what a feature control frame is?
Right. A feature control frame is how we actually convey those tolerance requirements on a drawing. It's a rectangle with compartments. It includes the symbol for the geometric characteristic we're controlling, like flatness or position, then the tolerance value, any material condition modifiers we might need, and crucially, any datum references.
Datum references? What are those?
Think of a datum reference frame as the skeleton of the part's geometry. It establishes a 3D coordinate system. It's typically 3 planes or axes that constrain the part in all 6 degrees of freedom, 3 translations, and 3 rotations. A datum itself is a theoretical, perfect feature, like a perfect plane or axis that we use as a reference point. The physical features on the part, like a flat surface or a specific hole, those are datum features. They help establish that reference system to ensure everything lines up.
Okay, so you're building a precise unmoving reference system on the part itself and then defining all other features relative to that. That makes a lot of sense for complex assemblies.
Exactly. And it's how you ensure that, say, a hole needs to be within a cylindrical tolerance zone of 0.1 millimeter, and it's referenced to 2 specific datums for alignment. That frame ensures the hole is accurately placed, and aligned within those required limits.
Now, you mentioned material condition modifiers earlier. What are those, and why are they important?
Material condition modifiers add flexibility to the tolerance requirements. The two main ones are maximum material condition or MMC and least material condition LMC.
So it's a smart way to give the manufacturer more wiggle room where possible, as long as the part still performs as intended. That seems very practical for production.
It is. And it all boils down to the core concept of GD&T, which is the tolerance zone. That's the designated limit within which a feature is acceptable. It could be a cylindrical zone for a hole's position, or two parallel planes for flatness, like with our mirror example. It allows minor variations but ensures correct functioning. That's where you put your tolerances where they're truly needed, preventing unnecessary tightness elsewhere.
So, looking at the big picture, Alex, why does GD&T really matter in modern manufacturing? It sounds like it's more than just a drawing standard.
It's way more. GDT is a powerful tool for communication between design and manufacturing teams. It ensures parts meet functional requirements without being over-toleranced, which, as we discussed, leads to significant cost savings, especially in mass production. With automation and precision becoming so critical, especially in industries like aerospace, medical devices, and automotive, GD&T ensures parts meet strict quality and reliability standards. It lets designers create parts that are easier and more economical to produce, inspect, and assemble.
That makes total sense. It sounds like it's a language that bridges the gap between theoretical design and the realities of the shop floor.
That's a great way to put it, Mia. Ultimately, GDT is about ensuring your design intent is perfectly clear and accurate. It helps focus on the functional aspect of parts, defining exactly what's needed to reduce ambiguities, increase quality, and lower cost. It's how we get precision parts.